Hello, and this is the recording for the workshop for firmware. This is the workshop number 2. So pretty much, I want to go over some additional things about the motor and how we would want to control the motor. So before I kind of just went over like a high level block diagram of what a motor controller looks like, things that we might have to do, things that we might have to interact with, and stuff like that. Now I'm going to go a little bit more in depth on how we can control or do the motor control. So this is the high level block diagram that I made before for a motor controller, right? So the main thing that, just to recap, the main place that we're going to be programming it is on the MCU, right? We're going to be writing the code to control the motor on this thing and pretty much write the algorithms, that we might need to, control this motor with. We're also going to take an input, and based on the input, call this algorithm and spin this motor, right? And some other things we might want to do with the MCU is communicate with other chips, or they're called integrated circuits, right? So example of one is our motor driver right here, right? We want to communicate with it, and we might need stuff for our motor driver. We might need stuff like SPI, or serial peripheral interface, which is just a way to pretty much interact with a motor driver. All right, so these are all things that we can expect to program. And I think, I'm not too sure if I mentioned this in the previous workshop or just like some other time. There's also 3 levels of difficulty where we can kind of approach you doing the firmware for this, right? And it's really up to your team to decide how hard you want to go in. All right, so the very first one is low level, right? Like super low level. So you implement everything yourself, right? You write all the algorithms yourself. You write all the control yourself, and pretty much start from absolute scratch using just the bare bones libraries that you might want to use, and implement everything for motor control. All right, and then there's also like a medium level. All right, so the medium level is kind of a little bit easier, right? So there's a great library out there called Simple FOC. I think I mentioned it last time, which we can pretty much use that implements BLDC motor control for us. All right, so all we have to do is use this library, and we will be able to control our motor. All right. Now, the caveat to that is we still need to do things like get our input, translate it to BLDC motor control, use SPI to communicate with our integrated circuits, stuff like that, right? But we don't have to implement absolutely everything from scratch, right? So the algorithms and stuff like that, we don't have to implement. But if we did low level, we would have to implement the algorithms and stuff. So Simple FOC is a great library that you might want to choose when considering motor control. And I'm sure there's other libraries out there that you can also look and try to reference. Now there's also a high level program that we have to our advantage, and it's called the VESC firmware. All right, so some guy pretty much had a standard set of hardware that he wrote firmware for, and we're going to pretty much follow the exact same hardware that he used. So if we want, we can really just flash the firmware on there, and this pretty much does all the work for us. We just can change parameters and stuff like that. All right, so with the VESC firmware, we're pretty much ready to go, as long as we use the same hardware, which we are. So all we can really do is change parameters, right? And, maybe change, like, kind of get used to the VESC tool that he has. All right, so there's 3 really, like, kind of levels that we have a chance to use, right? So low level is doing everything from scratch. Medium level is making use of libraries, but still taking in inputs, doing communication, stuff like that, to pretty much still do a decent amount of work, right? This is probably like the most recommended for learning, right? High level, we just plug in the wire and upload firmware, and then we might want to change parameters based on what we want, or like any changes we might make. So this is kind of the recommended, but honestly, it's up to your team on what you want to do. If you feel like you have a lot of time, go ahead and do low level. If you feel like, you might not have that much time and you really want to just get something working, feel free to do high level. It's really up to you guys. My recommended is medium level, perfect amount of learning, and you still get to code a lot of firmware and get really experienced with it. All right. Yeah, so other than that, let me go more in depth on motor control and stuff that we might have to do, right? Because I didn't really explain it too much last time. I just explained like, oh yeah, your motor will move based off the phases that you're going to change and turning on and off transistors. All right, so a really important part of motor control that I didn't really talk about is if I go back to this GIF right here of this spinning motor, right, is how do we know when to change the phases, right? Because beforehand, right, I was just saying, you know, when this blue crosses the middle, right, it's going to change blue so that it pushes it at the maximum amount and repels, and attracts the red a perfect amount too. If you look, maybe this phase right here and wait for it to turn blue. So this is red right now, it's repelling, and then it's going to turn off, and then it's going to turn blue and repel, right? Unfortunately, right, we don't, in real life, we can't just slice a motor in half and see blue and red phases and be like, oh, we're going to turn that phase on and off, right? So we actually need to know exactly where the rotor or the middle is, the rotating thing, right? And if you notice on this diagram here, there's something a little bit different. We have the A phase right here, the B phase right here, and the C phase, right? So there's only really 3 phases of the motor that we can really control, and we pretty much need to send those phases the specific signals to move this middle rotor part, right? So there's a lot of ways how we can figure out the rotor. And I'm pretty much going to go over the methods, with you. But first, I want to point out, I think which is the most important, is we only have 3 phases in a brushless DC motor, so A, B, and C, and this gives us a perfect, 120 degrees of commutation, right? Because these phases are 120 degrees out of phase, right? And it pretty much lets us move this motor, right? And if you notice, right, each one of these phases only has 3 states, really, right? And 2 main states where it's actually commutating stuff, right? So if you notice, right, each phase can only be blue or red, right? And then these 2 are attached, right? So there's only really 3 times 2, 6 states where we can actually be in, right? And that perfectly corresponds to how our transistors will turn on and off as well, right? There's only 6 states that our transistors will turn on and off, right, from. So what we really need to do is pretty much make a state diagram, right, of these 6 stages, right? So we go from one phase to another phase to another phase to another phase, and how we energize it, right? Yeah, so that was kind of my side tangent. And we need to change these phases in these perfect 6 stages that we have to pretty much move the motor, right? Or to move the rotor. All right, so there's multiple ways we can do this. So there's one way, which is called open loop control, and there's another one that's called closed loop, right? Now, open loop just means there's no feedback in our system, right? So imagine you're balancing like a baseball bat on your hand, for example, right? And you can probably do this really well, right? You just move back and forth, depending on where the baseball bat is going, you just move in the opposite direction to kind of keep it aligned, right? I should probably draw a picture or something. So like, here's me balancing a baseball bat, right? And as long as I move my hand back and forth, left and right, I can probably balance it really well, right? But imagine I'm blindfolded, right? And I can't see the baseball bat, right? If I can't see anything, right, I'm not too sure if the baseball bat's going this way or this way, right? And it's going to fall over pretty much after a while because I'm kind of just guessing where it's going, right? So what open loop means, right, is that there's no feedback. I'm kind of just guessing where it's going, right? And we can do the same thing for our motor, right? We might not know where the middle rotor is, but we can maybe just pretend like we know and just force it to go somewhere, right? And that's what open loop is. We're just kind of just guessing where the rotor is. Guessing rotor, and just kind of just trying to move it as much as we can, all right? So a closed loop is, I open my eyes, I take off the blindfold, and guess what? I can see the bat now, right? So that gives me feedback, right? And I kind of create this loop where I know where the rotor is. Known rotor. So I know where the rotor is, right? And since I know where the rotor is, I know exactly where I can send these signals, right? How do I know where the rotor is? Right? Again, there's no slice, right? So there's a lot of methods for closed loop, right? And usually closed loop is, more efficient, right? Because obviously if I know where the rotor is and I send it the exact signals that it needs, I'm gonna have the best amount of torque or best amount of power transfer into the rotor, into my motor, right? So open loop, we kind of just guess, right? We kind of just send these signals willy-nilly. We know we go for the 6 stages, but we don't know where the rotor exactly is. But closed loop is kind of like the holy grail of what we actually want to do, all right? So there's multiple ways we can do this, all right? And multiple sense methods. So one is called current sense, one is called back EMF, and one is Hall effect sensors. So let me explain current sense first. And I'm going to be referencing a simple FOC since it's a bit more, it goes a lot more in depth than what I understand for the thing. So it's a lot better if I just use this library. So this is an example of current sense, right? And it's actually kind of simple. So what they do is they put resistors in line with the BLDC motor, right? So right here is where the signals are getting sent, right? This UA is where the signals are getting sent, UB, UC. If we look at our diagram again, right, this is exactly how we move the motor, right? But we put a really small resistor in between this UA, UB, UC, and our BLDC motor in series, right? And we put an op amp between that. So what this op amp pretty much does, right, is it's able to measure the voltage across this resistor. If you remember your theory from like any circuit course, right? So I'm going to measure 1 point here, 1 point here. So it measures the voltage across the resistor, right? So if I know the voltage across the resistor, right, then what does that mean? What other parameter can I get? Well, the other parameter I can get is current, right? Just using Ohm's law. So by measuring the current going across each one of these resistors, right, we're actually able to pretty much sense where the rotor is based on that position, right? And this is a great diagram that kind of demonstrates that. So here's the low side current sense, high side current sense, and here's the inline current sense period, right? So pretty much I can see exactly where my rotor is and if either the phase is energized or not energized, pretty much. Yeah, that's pretty much all I really have to say about this for now. So simple FOC, right? Really useful. It gives pretty much the library on how they do it and what the object you have to make to pretty much make this work. Again, this is an open source library, so if you want to look in on current sense and how they implement themselves, you can take a look at that and how they process the signals. But pretty much they read the current over these phases, and based off of that, they're able to know where the rotor is, which is really, really cool. All right, so that's current sense done. So back EMF is a little bit different. So what they do for back EMF, right, is they kind of just measure what the phase voltage is on each wire. So if you remember what I said before about the phase wires, right, or about right-hand rule, right, whenever you induce a current through a wire, right, there's if you use the right-hand rule, so here is a current I. There is a magnetic field that's also induced in that wire that kind of goes, using the right-hand rule. So that's kind of what's happening here. So the opposite is also true, right? If the current is going backwards, right, an opposite magnetic field is going to be produced, right? And again, right, if we look at our motor, right, what can I say here? If the motor moves, right, if we induce a magnetic field, right, current will be produced instead, right? So if I induce a current, a magnetic field will be produced. But also the other way around is true. If I produce a magnetic field, current will be induced. And this is called back EMF, or inductive flyback, where we're pretty much able to see the back voltage of our phases, right? And because, our motor is moving, so we're able to sense this inductive flyback. So if you see right here, right, it's showing the inductive flyback, or the back EMF of our motor, and it's in very unique stages. And in fact, it's in 6 unique stages that we can read. So 1, 2, 3, 4, 5, 6, right? And we can read these 6 unique stages to pretty much spin our motor and know where the rotor position is, right? So if you get each phase, and based on each phase, you kind of combine it all together, right? You're able to actually sense where the middle rotor is. yeah, that's pretty much it for back EMF, right? So opposed to current sense, where we have a or we have an inline resistor, right, where we can measure the current across the BLDC motor. This one's just an analog signal that we're actually able to read off the phases, right? So we can just read the analog voltage signal there, and based off the analog voltage signal, we know where the rotor is. Yeah, that's pretty much it. If you have any more questions, because I think it's a bit easier to have a conversation about this on like how back EMF works, especially since I won't lie, I'm not the greatest at knowing how to implement this in firmware and stuff like that, but I kind of know the theory. I think it's a lot better to ask me, but pretty much we read the analog voltage and there's 6 states, so depending on what the analog value is, we know where the rotor is. Alright, cool, so that's back EMF. And last but not least, we have Hall effect sensors. So Hall effect sensors, again, it's in simple FLC again, right? And we can just set it up by, using the library. But pretty much what they do is they are able to sense whenever a magnetic field is there. So let's say here's a Hall effect sensor. And it's able to pretty much say, hey, there's a magnetic field that's being applied to me. But if the magnetic field goes away, then I'll be like, okay, no magnetic field, all right? So there's 2 states, right? It's on or off. So it's on if there's a magnetic field and off if there's not a magnetic field. All right. So if we look at this animation again, there's actually a Hall sensor signal that's right here. And it's actually really cool, right? Depending on whether it's a north pole or a south pole that's being applied to a Hall effect sensor, it's either going to be a 1 or a 0, right? So, so in this case, I said, like, if there's no magnetic field or there is a magnetic field, but in this case it's magnetic field is either going this way, right? So clockwise or counterclockwise, right? And depending on that, it'll be on or off. So if you see right here, we have a north and south pole, and again, the Hall effect sensor just detects a magnetic field pretty much. So if I let this play at the beginning, right? Let's see, at the very beginning, right, H1 is high. So if we look at H1, it's on the north pole, so it's high. If we look at H2, it's on the south pole, so it's low. If we look at H3, it's also on the south pole, so it's low, right? So based off only 3 Hall effect sensors that are 120 degrees out of phase, we're actually able to sense pretty much anywhere where the rotor is. And this is just a digital signal we can read, right? So if I pause again right here, right, this is blue, it's high, so H3 should be high, which it is. This is blue, H2 should be high, which it is. H1 is on red or south, so it should be low, right? And this just goes in 360 degrees, and we can pretty much read anywhere where the rotor is based off these digital signals, which is really, really cool, all right? And again, we see the 6 commutation steps right here, right? So here's one, right? So high, high, low, low, high, high, low, low, high, low, low, high, high, low, low, high, high, low, high. And that's 6 steps. Yeah, that's pretty much it. So you read these digital signals, and depending on these digital signals, you know where the rotor is. All right? Boom. That's pretty much it. So that's the kind of 3 sense methods that we can use for closed loop commutation. All right? And I would recommend, if you ever do have time and you want to know more, right, you can always go into simple FLC and look at like the theory corner to kind of see kind of how everything works and what that control algorithm is and stuff like that. All right, so this is the commutation methods of closed loop. So commutation methods. Let me just get rid of these scratches for you. So they're kind of the commutation methods that we can use to pretty much know where the motor is. Commutation sensing methods. All right. So there's also like multiple ways we can move the motor, right? Because we have to apply these voltages in a specific way, right? But there's also multiple ways to apply those voltages to the motor, right? So the 3 main ones, right? And I'm not going to go too in depth in this because I think it's pretty easy to find resources online that's better than me, to be honest. But the 3 main ones is trapezoidal, where you apply a trapezoidal pattern, sinusoidal, where you kind of apply a sinusoidal pattern to each phase, and also FOC, or field oriented control. Which is what the library on Arduino pretty much implements, right? So you apply these algorithms to these three phases, and this is your commutation method, right? So this is your sensing methods, and this is your actual commutation method, or pretty much moving a motor method. All right. I think that's pretty much it. So yeah, if you want to know more about these motor control methods, I think there's a link right here. I guess I'll link it on this video as well. That is like an actual study on like pretty much the commutation methods, benefits of each one of them, sense methods and stuff like that, like back EMF and field oriented control. And it goes even more in depth than simple FOC, and it's a great resource that I read over a couple times. All right. I think other than that, that's pretty much all I have for you for this one. I would recommend just looking into SPI a bit and like getting to know what it means and like how to use it. But this is pretty much your general what you're gonna do and the firmware that you're gonna write. All right. So just to sum up the steps, right? All you're really doing is getting the input, right? And this is kind of like your very short pseudocode. Based on your input, what are you gonna do? Well, you're gonna move your motor. And you know, to move your motor, you have to use your commutation sense method to know where your rotor is, and based on rotor position, move the motor. All right, and this is kind of like a closed loop feedback. You're gonna look at where your rotor is, move the motor. Look at where your rotor is, move the motor, so on and so forth. And that's all based on your input. All right. Other than that, I think that's all I have for you. If you have any questions, again, always feel free to ask. And yeah, thanks for listening. Bye.